Hi, so in this video, we will design new types of energy dissipation, right? So, energy basically we have to find out that energy dissipation depends on Froude number. Okay, so first of all, we say this. So as you can see, this is the table. This is the Hack 14, Hack 14 video. So it is the standard to the design of energy dissipation, right? So in the page number 14, you will find out this table, which define that the conditions to design energy dissipation, which type of energy dissipation you want to design. If we want to design, basically we are going to focus on CSU rigid boundary basin. So its problem should be less than 3, right? There will be sand category. This M means moderate. So load is moderate. Okay, that's the average. And length of the boundary, so that's the low boundary's length, and floating is the moderate. Tailwater is required, not needed. If there's no tailwater, so that's okay. So you can calculate your CSU, right? Then, so as you can see, and this energy dissipation will comes in the stream bed level dissipators, right? So we are going to analyze the CSU rigid boundary condition. And as you can see over here, okay. So this is staggered rows of surface elements to initiate a hard look jump, right? So you test the number of basins with different roughness configuration to determine the average drag coefficient over the roughness of portion of the basin. The effects of roughness elements are reflected in drag coefficient, that the force to drag the debris and water, yes, and the effects of the roughness elements are reflected in track coefficient that was derived empirically for each roughness configuration, right? So basically, we use to find out the drag coefficient in the CSU basin. So as you can see, this is the inlet, oh sorry, outlet of culverts that will pass, and there will be some kinds of buffalo balls towards that water will strike on this buffalo ball, then that will pass, and that will uh, outlet for water overflow will have less energy as compared to the outlet of uh, culvert, right? So as you can, this one is the section view. So what is coming over there, and this is the flow depth, and there that will strike on this buffalo wall, then again that will pass it, and that will flow becomes higher, and that will pass over there just like this. The height of the elements h must be between 0.3 to 0.91, the approach flow average depth by when that section will approach, so that should be that value by not, that should be 0.3 to 0.91 meter, okay. And the relative spacing L upon H between the rows of elements, these elements, this must be either 6 or 12. The latter is not severe restriction once the relative spacing is normally fixed parameter in the design, right? So these are the parameters you have to understand and understand. After that, you need to analyze it, right? Okay, the basin dragging coefficient, if there is a ratio of y upon h, y a 91 and L upon h it 6, so then that will be value 0.32, all right. So and it will automatically calculate by yeah, HY8. So just double click on your culverts, then go to energy dissipation, then select design external energy dissipator, then change it over here stream bed level structures, and CSU basin. right? We have a crowd number is less than 3 and must be either color concrete box or circular. We have uh, nice. As you can see, basin depth is 0.26 meter, okay, by a 0.26, and basin velocity 4.31, okay. The first row at W 12 meter, right? Divergence we are getting 2.545, right? So L upon H ratio is coming over there, so we are just getting 7.87, right? 14 elements with H by A 0.9 meter, there is, right? So as you can see, we will get all results as per our requirements, and it is satisfying the results, right? So as you can see over here, so we are just we have 4 rows with spacing equal to 6 and 14 elements with h by upon a 0.91. So as you can see, we will get our CV coefficient, basin drag coefficient CV. So that value is 0.91. We have h by y ratio 0.91 and L upon h ratio is 6. So we will get n 0.21 because we have elements 14, okay, and our rows is 4. That's why we are getting 0.21 drag coefficient, right? As you can see, this one is over 0.21, right? So as you can see in the drawings, there's a, okay, so we'll listen this y naught, okay, and this is the basin depth by a, this one is basin depth, right? And we have a basin velocity 4.31 meter per second by VA, right? And first row at 2, that's 12 meter, width is coming or not, okay, that is 12 meter, right? And basin width WB, as you can see, this one, right, WB, this one is WB, okay, that is coming 12 meter, okay. And basin length LB, we have to, as you can see over here, this one is length, basin length LB, that is 43 meter, okay. And as we have shown you, by V basin depth by V, this one is value, that is outlet value that is passing to the basin, so that is coming 0.52 meters, okay. That is outlet velocity by V 0 point or 2.94, almost 3 meter per second, right? And row spacing, that is spacing, we are just providing that is spacing 7.87 meter is coming, okay. And this is the height 1.3 meter, that is height of the elements, we have to provide 1.31 meters. And the width or spacing, that is width, we have to provide, that is width 3.42 meter we need to provide, okay. This is the exit depth YC, that is critical depth 7.5 meters, and exit velocity 2.714 meters, right? There's, okay, so we have to define it and find out the values, right? You have to follow these equations and these drawings to assign your parameters and prepare the drawing, and this is on page 158, right? You can find it out to design the CSU rigid basin, right? Thank you.